Hello. I'm hoping everything is working, but I'm gonna do this room on TryHackMe. I'm gonna try it at least. Okay. So basically, we're just gonna start the attack box. I'm gonna read the introduction. In this room, we aim to exploit simple stack buffer overflows without any mitigations on x86 to 64 architecture Linux programs. We will use RAID R2 to examine the memory layout. You are expected to be familiar with x86 architecture and R2 for this room. We have included a virtual machine with all the resources to ensure you have the correct environment and tools to follow along. To access the machine, visit SSH. System secure shell, use the following credentials: username user1, password user1, password. So that's going to be our first step. Start the machine, connect to the network via SSH. Just going to wait for this stuff to load. I'm going to keep reading while we have to wait for this actually. It's going to go into some speech here. When a program runs on a machine, the computer runs the program as a process. Currently, computer architecture allows multiple processes to be run concurrently at the same time by a computer. While these processes may appear to run at the same time, the computer actually switches between the processes very quickly and makes it look like they are running at the same time. Switching between processes is called a context switch. Since each process may need different information to run, e.g. the current instruction to execute, the operating system has to keep track of all the information in a process. The memory in the process is organized sequentially and has the following layout. Higher memory addresses, the user stack is going down, it seems, shared library regions, runtime heap going up, read/write data, read-only code/data. Let's see here. Let me select this. I can get SSH into the server. User stack contains the information required to run the program. This information would include the current program counter, saved registers, and more information. We would go into detail in the next section. The section after the user stack is unused memory and is used in the case the stack grows downwards. So this is unused, I think is what it's saying. It's downward. Shared library regions are used to either statically/dynamically link libraries that are used by the program. The heap increases and decreases dynamically depending on whether a program dynamically assigns memory. Notice there is a section that is unassigned above the heap, which is used in the event that the size of the heap increases. The program code in the data stores the program executable in initialized variables. Okay, so we have where is dynamic allocated memory stored, where is information about functions, e.g. local arguments stored. Let's see, they're both going to be here, I'm saying. Let's see. We can also do this while we're waiting. Connect to our network. Here we go. Is there any SSH? Oh yeah, that's right. Yeah, SSH. I don't remember if there's any commands for this. I think I might have to do like UNP, right? Maybe not though. Okay, maybe not. Password is gonna be user1 password. Yeah, I fat fingered it. I knew it. Let me pull this up on the side here. Hold on. Alright. User. Oh no. Let me just restart this. User1 password. That should work. Interesting. Oh, it's because I'm logging into root. I think I have to do something like this, maybe. I'll just verify it if not. Host port for login name. Maybe I can do /help SSH. See if there's maybe, oh no. What? Okay, okay. That's great. Let me just, hold on. Second here. This over here. Alright, my bad. Seems like I'm brain dead. I forgot how to fucking connect to a server. Actually cooked. That's what I mean. It's kind of been a minute. I've been kind of out of my element for whatever reason. I've just kind of been reading about programming mostly. This should be good. Oh, I cucked it. My bad. Hold on. I hate this keyboard so much. What? I'm just gonna copy and paste it. I'm done. I hate this keyboard. Yeah, that's right. I was looking for the one on ActiveBox. It's in a different spot. This should work. What? Permission denied. That makes no sense. Maybe I typed in SSH user 1. Oh yeah, I definitely typed it in wrong. That's why 4218. That should be good. There we go, finally. Alright, complete this first step. And then we can go back to this question. So, I'm gonna read this again. User stack contains the information required to run the program. The information would include the current program counter, saved registers, and more information. We will go into detail in the next section. The section after the user stack is unused memory, and its use case in the stack, and it's used in the case the stack grows downwards. Shared library regions are used either statically / dynamically. See, this one's confusing though, because it's a 4-letter word. But it's saying right here that shared library regions are used either statically / dynamically to link libraries that are used by the heap. Oh, the heap. Makes sense. And then this is going to be the stack, obviously. Yeah. Alright, so I'll keep reading this from where I was. Save registers more information. We are going to detail. The section after user stack is unused memory and is used in the case the stack grows downwards. Shared library regions are used either to statically / dynamically link libraries that are used by the program. The heap increases and decreases dynamically depending on whether a program dynamically assigns memory. Notice there is a section that is unassigned above the heap right here, which is used in the event that the size of the heap increases, which makes sense. The program code and data stores the program executable and initialize variables. Alright. x86 to 64 architecture procedures. Stack bottom at higher memory address. Stack top at low memory address. A program would usually comprise of multiple functions, and there needs to be a way of tracking which function has been called and which data is passed from one function to another. The stack is a region contiguous memory addresses. Contiguous memory addresses, and it is used to make it easy to transfer control and data between functions. The top of the stack is at the lowest memory address, and the stack grows toward lower memory addresses. So hold on, let me read that. The top of the stack is at the lowest memory address, and the stack grows towards lower memory addresses. The most common operations of the stack are pushing, used to add data onto the stack, and popping, used to remove data from the stack. Push var. This is the assembly instruction to push a value onto the stack. It does the following. Uses var, or a value stored in memory location of var, stack bottom, stack top, memory location 0x8, RSP points here. Decrements the stack pointer known as RSP by 8. Writes above value to a new location of RSP, which is the new top of the stack. Stack bottom, var, stack top, memory location x0, 0 RSP points here. Pop var. This is an assembly instruction to read a value and pop it off the stack. It does the following. Reads the value at the address given by the stack pointer. Stack bottom, variable, stack top, memory location at 0x RSP points here. Store the value that was read from RSP into var. Increment the stack pointer by 8. It's important to note that the memory does not change when popping values of the stack. It is only the value of the stack pointer that changes. Each compiled program may include multiple functions where each function would need to store local variables, arguments passed to the function, and more. To make this easy to manage, each function has its own separate stack frame where each new stack frame is allocated when a function is called and deallocated when the function is complete. Stack bottom, stack frame 1, stack frame 2, stack frame 3, stack top. This is easily explained using an example. Look at the two functions. Integer add, integer a, comma, integer b, integer new equals a plus b, return new, integer calculate, integer a, integer b, integer final equal add, comma b, return final, calculate 4 and 5. What direction does the stack grow, lower or higher? Use the symbol. I think it's definitely going to be lower here. Am I wrong? Oh no. Is it low? It's higher? Let me just copy whatever symbol they got going on here. Do they want it in these quotation marks? I'm so confused. Hold on, probably. What? Okay, I'm just gonna try all of them at this point. Like, I'm so confused. Here's the sign. Here's an I. L. What is this? It was an L? Oh my god. That is terrible. What data is push? Alright. Procedures continued. This explanation assumes that the current point of execution is inside the calculate function. In this case, calc is known as the caller function, and add is known as the callee function. The following resembles the assembly code inside the calc function. So we have system calc 37, system.calc. This is basically our main for assembly from what I know. Integer argument 1, integer argument 2, variable integer, local. See, they kind of lost me here. I just see they're defining variables basically. Call xrf from system.main, which is up here. Wait, I thought it was up there. It's not. Okay, 0x call xref from system.main 0x562b 771356 56. None of these ends in 59 though, so I don't know, unless it's never used RD2 before or whatever. But push Q, RBP, the pointer or the register. Yeah, I need to know way more about assembly. This is like something I need to learn. Stack bottom, previous stack frame for a function calculation, and stack top. So that's all it wants me to see basically, is this is the stack. No, hold on. The add function is invoked using the call operand in assembly. In this case, call q sim.add. Where's that at? Okay, it's not even here then. It's kind of like that, but call q.simadd, the call operand can either take a label as an argument, e.g. a function name, or it can take a memory address as an offset of the location of the start of the function in the form of call value. Once the add function is invoked and after it is complete, the program would need to know what point to continue in the program. To do this, the computer pushes the address of the next instruction onto the stack. In this case, the address of the instruction on the line that continues move percentage exal local underscore 4h. After this, the program would allocate a stack frame for the new function, change the current instruction pointer to the first instruction in the function, change the stack pointer's RSP to the top of the stack, and change the frame pointer RBP to the point of the start of the new frame. Getting confusing. Stack bottom, previous stack frame for calc, return address. So let's see how it changes then. Stack frame for calc says for the function. Once the function is finished executing the call return instruction, I'll return Q. This instruction will pop the value of the return address of the stack, deallocate the stack frame for the add function, change the instruction pointer to the value of the return address, change the stack pointer's RSP to the top of the stack, and change the frame pointer's RBP to the stack of the frame of calc. Okay. Now that we understand how control is transferred through function, let's look at how data is transferred. In the above example, we save that functions take arguments. The calc function takes 2 arguments, A and B. Up to 6 arguments for functions can be stored in the following registers. Interesting. RDI, RSI, RDX, RCX, R8, and R9. And I'm going to copy this real quick and just put it in a note, just so I don't remember it, or don't forget it, I meant. Note RAX is a special register that stores the return values of the functions, if any. If a function has any more arguments, these arguments will be stored on the function stack frame. Give me 1 second here. I'm going to pull up my stream. Stores the return values of the functions, if any. Alright. If a function has any more arguments, these arguments would be stored on the function stack frame. We can now see that a caller function may save values in their registers, but what happens if a callee function also wants to save values in the registers? To ensure the values are not overwritten, the callee values first save the values of the registers on their stack frame, use the registers, and then load the values back into the registers. This caller function can also save values on the caller function frame to prevent the values from being overwritten. Here are some values, rules around which registers are caller and callee saved. RAX is caller saved. RD, RSI, RDX, RCX, R8, and R9 are called saved, and they are usually arguments for functions. R10, R11 are caller saved. RBX, R12, R13, R14 are callee saved. RBP is also callee saved and can be optionally used as a frame pointer. RSV is callee saved. So far, this is more than a more thorough example of the runtime stack. I want to see how they use these here though, like RDI. They have ESI, they didn't go over that. RBI. RBP. Callee saved and can be optionally used as a frame pointer. Push Q, RBP, frame pointer. Yeah, I need to read more about this. So far, this is a more thorough example of the runtime stack. Empty argument N, under empty argument 7 return address, say registers and load and local variable. What register stores the return address? Stores the return address. I feel like I have that in my notes. No way. Return address. Oh, I think it's racks. There we go. Endian, I don't know how to say this word, but I know what it means. Endianness. In the above programs, you can see that the binary information is represented in hexadecimal format. Different architectures actually represent the same hexadecimal number in different ways. And this is what is referred to as endianness. Let's take the value of 0x 1, 2, 3, 4, 5, 6, 7, 8. As an example, here the least significant value is the rightmost value, 78, while the most significant value is the leftmost value, 12. 78, 12. Little endian is where the values arrange from the least significant byte to the most significant byte. Big endian where the values arrange from the most significant byte to the least significant byte. Here each value requires at least a byte to represent as part of a multi-byte object. Interesting. Now that we've looked around at all background information, let's explore how overflows actually work. If you take a look at the overflow 1 folder, you'll notice some C code with a binary program. The goal is to change the value of the integer variable. From the C code, you can see that the integer variable and character buffer have been allocated next to each other. Since memory is allocated in contiguous bytes, you can assume that the integer variable and character buffer are allocated next to each other. Note, this may not always be the case with how compilers and stacks are configured. If variables are allocated, they would need to be aligned to particular size boundaries, e.g. 8 bytes, 16 bytes, to make it easier for memory allocation / deallocation. So if a 12-byte array is allocated where the stack is aligned for 16 bytes, this is what the memory would look like. 0 buffer, padding 12 bytes, 6 bytes at the end. So the compiler would automatically add 4 bytes to ensure that the size of the variable aligns with the stack size. From the image of the stack above, we can assume that the stack frame for the main function looks like this. Stack bottom, save registers, volatile int variable, char buffer 13 array, buffer 0, character, argument vector, integer, argument vector, stack top. Even though the stack goes downwards, when data is copied / written into the buffer, it is copied from lower to higher addresses. Depending on how data is entered into the buffer, it means that it's possible to overwrite the integer value. From the C code, you can see that the gets function is used to enter data into the buffer from standard input. The gets function is dangerous because it doesn't really have a length check. This would mean that you can enter more than 14 bytes of data, which would then overwrite the integer variable. Try to run the C program in this folder to overwrite the above variable. What is the maximum number of characters needed? You can enter more than 14 bytes. So we're gonna go to this folder. I'm way too used. That's embarrassing. I've been using way too much Windows. So we have. Make this a little clearer. I have here int overflow C and then int overflow. So unfortunately we don't have nvim, but we're just gonna take vim here. That was a complete accident. I'm gonna look at the .c file. We're gonna look what's going on here. We have hashtag include studio.library.header hashtag include. I kind of don't know what this is, but it's just another header file. Hashtag. Actually, let's just look it up. Just look it up. unistd-h is a standard header file in C and C++ programming that provides access to the POSIX operating system API. It is a fundamental component for developing applications on POSIX compliant systems, including Linux, Mac OS, and other Unix-like systems. The header file declares a variety of functions, symbolic constants, and types related to the system calls and operating system services. Some of the key functions provided by unistd-h include functions like read, write, close, lseek, pipe, excel, xle, exec, cvp, exec, vector pointer, probably fork, exec, exit, get, PID, I mean, these are stuff I should know for sure, definitely. Unfortunately, I don't though. Include studio.header information, integer main, integer argument character, char, Double R. What is the 2? Usually I see them like char and then 1, and it means like a string of characters. But what is? I wonder what the 2 means here. Volatile int variable equals 0. Char buffer 14. Gets buffer. If variable is equal to 0, then printf you have changed the value of the variable. Else printf try again. Alright, well let's just take this information 14 and start out with 14. This shouldn't work, I don't think, because it says this would mean you can enter more than 14 bytes of data. So I mean, but 14 should be the test, I feel like. So that's what we're gonna do. We're gonna test it with 14 and then we'll try 15. Alright. The little WQ, and then do I actually have to like recompile the I definitely do, don't I? Hold on. One second here. See here. Alright, we can just hopefully if they have GCC on here we should be able to do this. Overflow. Oh, that's why. Overflow, and then we should be able to do and overflow. Hold on. Yeah, it should just be this. What? Overflow.c no such file or directory. Oh yeah, that makes sense. Warning? Oh. Implicit declaration function gets. Did you mean f gets? Gets is function and should not be used. Did it work though? Like, I get it's dangerous. No, it didn't work. Oh, that's weird. How do I want to test it though? I feel like I can definitely test it because wasn't he? Oh no, I didn't mean to do this. Let's just see, like, f gets. Where is gets? Do I need to change it to f gets? Is that like some new shit for whatever reason? Let's try. Just recompile this shit. I mean, I don't know why that would matter at all. Yeah, see, now f gets isn't gonna work. Like what? Bruh. What is this, man? It's supposed to be simple. I like not. Is it just... I'm gonna look at their code here. Gets. I mean, it's like the exact same thing. If variable equals 0 gets buffer. But their gets is all colored up. Mine isn't. Wonder if there's like a reason. Nah, never mind. It's right. Does it compile when this is set to 0, or does it just want you to understand like how the buffer works? Maybe it doesn't want me to do this. That could be why. Like, even if I do that, like that should compile. Okay, perfect. Alright, so yeah, it's just not gonna compile. I'm just gonna change this to 15 because like the buffer is 14. If you overflow the buffer, it crashes. Like that's how buffers work. So it's 15. For this example, look at the following folder 2. Inside this folder, you'll notice the following C code: void special, meaning this isn't even going to happen. Print, this is the special function. Print F, you did this. Friend, void normal. Or not, this isn't going to happen, but this is the normal function. Why is this here? Integer main, integer argument, character argument, array vector, volatile integer, array new pointer, normal, char buffer 14 gets. Ooh. Similar to the example above, data is read into a buffer using the gets function, but the variable above the buffer is not a pointer to a function. A pointer, like its name implies, is used to point to a memory location, and in this case, the memory location is that of the normal function. The stack is laid out similar to the example above, but this time you have to find a way of invoking the special function, maybe using the memory address of the function. Try invoking the special function in the program. Keep in mind that the architecture of the machine is little endian. Alright, let's see here. We can do this. I'm gonna cd back, ls, cd overflow 2, I'm upset, and then we're gonna vim func pointer. Of course I did that. Alright. So the way of the normal from the stack is laid out similar to the example above, but this time you have to find a way of invoking the special function. The special function. So first you have to find it, pretty much. This is the special function. Interesting, okay. That was pretty easy. By the time you have, but this time you have to find a way of invoking the special function, maybe using the memory address of the function. That's cool, that's cool, that's cool. Let's see, I'm gonna look up how to find the memory address of a special function. Let's see what it says here. To find the memory address, you use the address of operator with the function's name without parentheses. That gives you a pointer to the function which holds its memory address. You can then use the address using the %p format with the specifier printf. So the AND address of my function and my function return. Invoke the special function. I don't think I'm really getting it here. From the example, this makes like no sense. Yeah, it's got me on a fucking loop, man. This shit's brain dead. No, get me out of AI mode. I just want some information. Special function registers are in the upper area of address memory from address 0x80 to F. Area of memory cannot be used for data parameters. Instead, a series of memory map ports and registers. Maybe using the memory address of the function. Alright, hold on. Let's see. Let's see. Oh, wait. They probably wanted me to use RD2 also for the other machines. Like the other folder I meant. That's probably why GCC wouldn't compile it. That makes sense. Integer main. Okay. Let's see if I can get in here. so I think I don't have to do the printf, so I'm probably not gonna do that. Or do no, yeah. I'm just gonna do printf here, and I should just do like, oh damn, address, or just like AD. What's it called up here? Special. I don't know how it's spelled. Is it capital or what? No, it's, well, oopsie. No, it's all lowercase. Special. And then we'll do like this for the, let's make sure. Depends in programs. Function C is used to format and print a memory address in hexadecimal format. Mathematics if a P can represent probability. Pointer. Most common usage, it prints the memory address stored in the pointer variable in the hexadecimal format, typically 8 digits long. So yeah, then if that's the case, we should just be able to throw a new line on here, do a comma, and then grab special, and I think, hold on. It's the way it's set up here. I have to do a little different. Like, also these kind of wrong. Like, hold on. There we go. And then we do like void. And then we'll do special here. And then that. And I mean, I wonder. I'm just gonna, I don't know too much on how to like, usually I'll just compile it and run it, but it won't. GCC is not compiling these programs. Like, do I have this RD thing? No, doesn't even look like it. I probably don't even need it, right? But here we go, right there. In GDB, so maybe I think maybe I could open. Oh, here we go. I'm in GDB now. Kinda. All right. Remember these commands real quick. All right, so we'll do. Oh, I forgot I have to type quit. So we're gonna do gcc-g, gcc-g, func pointer dash func pointer dash c. So yeah, I don't know. I wonder. I'm just gonna make sure I'm not like missing something, because it kind of makes me seem like I'm not doing it right. And I'm gonna test probably the other file too at this point. Oh my god, this file is unbearable. Why won't it scroll? Great. Alright, I just want to check if this is right. we're gonna see, at least if my answer is right. Says it's, so yeah, it won't, it's basically just unsafe, which is why it won't. So also get S is unsafe and doesn't move from C because it allows buffer overflows. In your new code, in your code it can overwrite new pointer. Yes, your code is programmatically and semantic. So yeah, I mean basically they won't compile because they're not really safe anymore, which makes sense, but it seems like they work. We got here, for this example, let's look at overflow 3. Inside this folder, you'll find the following C code: void copy underscore argument, char array of string, string character buffer array of 140, string copy buffer string, print f, string / new line buffer, return 0, integer main increment argument character, comma character array vector, print f. Here's a program that echoes out your input, copy argument vector 1. Example will cover some of the more interesting and useful things you can do with the buffer overflow. In the previous examples, we've seen that when a program takes user-controlled input, it may not check the length, and thus a malicious user could overwrite values and actually change variables. In this example, in the copy underscore arg function, what's that at? Right here. Copy underscore arg function, we can see that the string copy function is copying input. String copy, we need to find that. So we have copy arg, string copy. It does not check the length of the data being input, so here it's also possible to overflow the buffer. We can do something more malicious here. Let's take a look at what the stack will look like for the copy underscore arg functions. The stack excludes the stack frame from the string copy function. Earlier we saw that when a function, in this case main, calls another function, in this case copy underscore arg, and needs to add the return address on the stack, so the callee function copy underscore arg knows where to transfer to control to once it has finished executing. From the stack above, we know that the data will be copied upwards from the buffer 0 to the buffer 140. Since we can overflow the buffer, it also follows that we can overflow the return address with our own value. We can control where the function returns and change the flow of execution of a program. Very cool, right? Definitely. Now that we can control the flow of execution by directing the return address to some memory address, how do we actually do something useful with this? This is where shellcode comes in. Shellcode quite literally is code that will open up a shell. More specifically, it is binary instructions that can be executed. Since shellcode is just machine code in the form of binary instructions, you can usually start by writing a C program to do what you want, compile it into assembly, and extract the hex characters. Alternatively, it would involve writing your own assembly. For now, we use this shellcode that opens up a basic shell. So why don't we looking at actually executing the shellcode? The basic idea is that we need to point the overwritten return address to the shellcode, but where do we actually store the shellcode and what actual address do we point it at? Why don't we store the shellcode in the buffer? Because we know the address at the beginning of the buffer. We can just overwrite the return address to point to the start of the buffer. Here's the general process so far. Find out the address of the start of the buffer and start address of the return address. Calculate the difference between the, hold on, I need to just fucking, can't read any of this shit. Find out the address of the start buffer, the buffer, and the start address of the return address. Calculate the difference between the addresses so you know how much data to enter to the overflow. Start by entering the shellcode in the buffer, entering random data between the shellcode and the return address, and the address of the buffer and the return address. In theory, this looks like it would work quite well. However, memory address may not be the same on different systems, even across the same computer when the program is recompiled, so we can make this more flexible using an NOP instruction. An NOP instruction and a no operation instruction. When the system processes this instruction, it does nothing and carries on execution. An NOP instruction is represented using \x90. Putting NOPs as part of the payload means an attacker can jump anywhere in the memory region that includes an NOP and eventually reach the intended instructions. This is what an injection vector would look like. NOP sled, shellcode memory address. You probably noticed that shellcode memory address and NOP sleds are usually in hex code to make it easy to pass the payload and input program you use Python. Python-c print NLP no over p plus shellcode plus random data array no over random data plus memory address. Using this format would be something like this. Using this format would be something like this for this challenge. Python-c. In some cases, you may need to pass zargs before dash program name. Use the above method to open a shell and read the contents of the secret file.txt. Okay. Does this just work or what? Okay. Did it copy though? No, that makes sense anyway. Let's see if this works immediately. Alright. Python-c print. This is confusing me. So I never looked at number 3. That could be why. I guess that's not really what I meant to do, but include studio void copy underscore arg character string character buffer 140 string copy buffer and string print f string new line buffer return 0 integer main integer argument character. See, so they say it's because the buffer basically won't happen because it doesn't, or it happens because it doesn't check this string. I need like more. What am I supposed to do? Let me see here if I can like get any more context. Let's see here. Buffer. So this is vulnerable. Let's see. So we're trying to abuse basically like the string and how many bytes are saved into it because the buffer doesn't, or the copy argument doesn't check the string. I think. So basically to overflow it, we need to write 140 bytes to the buffer, 8 bytes saved, RBP, which is going to be, that was on the previous page, but RBP was here. No. BP is also callee save and can be optionally used as a frame pointer. And overwrite the return address by 8 bytes. Alright. Let's see here. It's a pretty good little learning experience. I really want to get in more deeper into machine, or not machine learning, assembly and machine code. But okay, so string copy does not length check string. The buffer 140 is a local variable that sits on the stack. Overflowing buffer lets us overwrite the return address. Let's see. Alright. So it shows that they should all be good. I think we just gotta compile it basically. Pretty much. It's showing that it can't compile actually, like on hopefully it does though. Stack, I don't want to type it out. Stack no and then it's gonna be what is it? Overflow 3. I didn't know one of this. Just trying to avoid this. Buffer overflow.c. No, hold on. Then it goes to overflow. What? Oh man, I gotta go all the way up again. Oh, -3, and then it's gonna be .c. I knew this was gonna happen. Like, yeah, it states that like nowadays, because stuff's not the same, that you have to add here, include, you need st string.h, saying you need this, and that basically, man, I'm so used to like having a little bit of fucking mouse functionality. Vim, I use NeoVim, like, which I can still use my mouse. What? Let's see if this works. Copy _arg. See, it still won't compile. Let's see. If I cd overflow 3 ls. Yeah, I was about to say there's no way. I'm just gonna go back to normal. Oh, that could be why this didn't work though. Just gonna remove this, because it probably doesn't want us to change this code too much. Let's turn 0. Let's see. This part is like getting me so confused, man. I'm gonna try to compile it again and just see how this works. Let's see if this works. I mean, nope. Nope, nope, nope. Run the program inside GDB. Put a break at copy underscore arg. Alright, we're just gonna run like this real quick. We'll sample input. Let's see here. Now we're gonna print the buffer. Oh my, I would spell buffer wrong. Huh. Can't even find it. If I do info frame, should be able to get it here. Try to do this maybe. 0x/. it's not helpful. Alright, I might have ran the command wrong. XG money RBP X90. Here we go. That is beautiful. Can finally see what's going on. Alright. Nice, nice, nice. So we're looking for the RBP90 here. It's gonna be first column. Pretty sure this is it. Kind of spooks me, but because I don't know how like correct it looks. But let's try p void array. Oh wow, this is like this car array and money RBP dash 0x90. What? Syntax error. There. Oh. That's why. There we go. That's what we want. Alright, we're gonna see if this works now. Open a new shell, do Python 3-C import, hold on, import sys dot stdio dash buffer dash write slash b x90 comma 30 plus b. Oh, okay, I might. Let's see, I'm just gonna try this out real quick. See if this is right. No such file or directory. What? Let's see. This directory doesn't even exist. Wait, why am I? Oh. Yeah, I have to do it in here because I have to SSH out. Alright, in. I'm brain dead. Hold on. Get this back here. That's the goal, right? Here's a program that echoes your output. What? I can do this. Slash. Permission denied. Segmentation fault. No. It's not what I wanted. Let's see if this works. Try this out. I ran the command like twice. That's seg fault. Python 3 isn't found. Object has no attribute. Seg fault. We love seg fault. This. What the hell? What? I don't even know. So confused how that's happening. It's clear. I don't even think I have Python 3. I need to download Python 3. It's crazy. So I'm just tripping. Oh wait, I don't know the pseudo password, do I? shell, man. Check my notes here. Let's see, this should work. Oh no. Still didn't work, man. Here's a program that because you outplace close field and fire object destructor. Sys.accept hook is missing. Alright, man. Need GDB. This again, bro. Alright, let's go, let's break, copy, underscore, break, copy, let's go arg, breakpoint. Let's see here. Let's see here. Just gonna copy and paste this. Maybe I. Oh my god, it's so annoying. Maybe I did wrong last time. Nah, this isn't gonna work. I mean, it didn't work last time. Yeah. Info address buffer. Let's see. This is rough. This is rough. Hold on. getting stuck at the end here. See if this works here. Run command not found. Like what? Let's see, let's see. see. This shit is so annoying, man. There we go. This should. Oh, interesting. Okay. Figuring this out. I hope. Let's see, man, if I can get this right. Alright. Try to see if this will work. The rest of this just in here because I don't feel like typing it all out, to be honest. And then we can see if this works, I guess. I'm gonna copy these down if I don't forget them. fun little challenge though, I'm not gonna lie. Let's see here. Oh, let's not even do that. We can just. Oh, we kind of have to. So we just do Python. We do this here. Let's see. I am kind of confused here. It's a little bit. Just like make sure before I fuck up. Let's see if I press enter. Alright. I don't think it's working though. Let's try this. Pause. Invalid syntax. What? That's the only bad one. Just gonna SSH in again, low key. Just so I don't have to close that session. What is it? User one password. Yeah. Okay. So now we can cd buffer plus cd overflow for gdb buffer. I should be able to just do let's see, RSP, no registers. Wonder if I didn't do it right. That's not good. see if this lease works. No registers. Huh. Here, let's try this. Just quit real quick. Clear GDB. Go right back into it. Let's do break. Copy arg. Let's do the start. And then let's do run. Money sign. Python 3. I need a normal Python though, I think. I don't think I can use Python 3. Just gonna use this. Just cause I know this is right. Oh fuck. There we go. I'm just gonna use this on Python, so it's all the same, kinda. Just gonna do that. Make sure I don't fuck it up. Run.python.c. Yeah, that's right. Okay. Breakpoint 1. Copy R. 1, 2, stop. And then do this. Yeah, hopefully this works now. Alright, it's promising. Let's see here. Oh, my shit looks fucked up. Yeah, I think this is like low-key cooked. syntax. Yeah. Damn, man. Could try this. I swear I pressed Control D like so many times. I just Control D out of the fuck. That's great. What is Overflow 3? Like, did I make this on accident? Three. Fuck, let's just try it, bro. Just follow the same shit. I don't even know how I made this. Do break, copy. Mr. Arg. We're gonna do run. Money. Python. Hold on. Man. Try this. Python. Excuse me. This is gone on for too long, bro. I gotta be so bad. 158. Alright. Bro. No way I spelled Python wrong. Yeah. There we go. Of course, bro. It's over here like you're trash. Hop off. Actually, so bad. Alright, so these bytes, we overflowed the system basically. So that is where so we know that with 158 bytes, you overwrite the 6 byte long return address. This means the total input size that causes the return address is overwrite. So 158 bytes, the return address is 6 bytes long. Uses only 6 significant bytes to offset right before where your NOP sled. Shellcode must go as 100-56, 100-158-6 equals 152. So the buffer is 152 bytes before the return address. That's where you insert your payload. This helps you know exactly how to build your payload. Byte 6 will overwrite the return address. You replace a 152.6 with your actual shellcode and NOP sled. Okay. And then I need to do this one. Huh. Mine. Okay. And so okay, so alright. What the fuck? Where's the other Brandon? tripping? It was not that number. Yeah, no, it wasn't. What the hell? Alright, I'm just gonna quit real quick and just erase my notes and see if I can just restart this a little bit. Like GDB Q Buffer Overflow 3, and if I just do, I think it's already in. No, it's not. This first command and this second command. Well, I should just write them down. Not write them down, but put them in my notes. Oh, hold on. Okay. Alright, so we definitely gotta do this first. I'm so brain dead. We're gonna do this. Go here. I'm gonna paste this. We're gonna paste these 158 bytes. So this is our output. Basically all this, but we have to get the right numbers, basically, because you have to build the payload. It's like, I'm so bad at this, man. I wish I could be better. And then basic, oh no. Yeah, we'll just do this, and we're gonna run 159. Let me check something. Alright, yeah, I'm just gonna do this. Hold on. So we have our first number. Let's just go back into it. And let's do. Oh no. So then we can paste this, and this should give us this number. Alright. And then now I gotta figure out what to do with these numbers, basically. see here if I do. First I want to quit. And start it back up. No registers. Oh, let me try this. Oh my god. Hold on. Should just try it like this. Like, I'm actually brain dead. Alright. Go here. Boom. What? How did that happen? Makes no sense, bro. Alright. Run. Okay. Run. Alright. And then we do boom, 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 boom. And this works, please. Let's go. Let's see if anything. It doesn't look right at all. Bro, I'm cooked. I don't even know. It's stored around here. Yeah. What? No, it did not just expire and terminate. What are you talking about? Oh, it actually did. I'm cooked. No. No. That's cooked, bro. It's actually cooked. She's so cooked, man. Hold on, give me 1 second. 1 second. I should be good. Hold on. There you go. Man, I'm salty though. I'm really, really salty. Know why I can't do this one, man. This whole ass part is just so confusing. I'm so bad at fucking assembly. I need to read a book or something, bro. Like, I don't even know. Fuck. Hold on, I'll give it like one more try. I really don't know what to do. Got a few chance. No. What? Oh my god, I'm brain dead. User 1, bro. What? Oh. Huh? Ah, I did it backwards. Bro, there's no way. Oh, that time is actually just wrong. Bro, what? Okay. Type shit. I get it. That's how it is. User 1. Alright. I can't tell if it's there, bro. There we go. Alright. Let's go. Let's go. Alright. Let's get in this shit, man. Oh, fuck. Okay. Let's just go back. Maybe reread it a little bit. Alright. Where did it start off with this? Start shit. Yeah, right here. For the example, look at the overflow. Let's just look at it now. Let's just look at it now. Alright. 140 byte. Okay. The example cover is some more interesting useful things you can do with the buffer overflow. In the previous example, you see when a program takes user controlled input may not check the length. And thus a malicious user could override values and actually change variables. In this example, in the copy underscore argument function, we can see that the string copy function is copying input from a string, which is argument1, which is a command line argument. If a buffer of a length, a command line to a buffer of a length 140 bytes. But the nature of string copy is not change the length of the data being input. So here it's also possible to overflow the buffer. We can do something more malicious here. Let's take a look at what the stack will look like for the copy underscore arg function. The stack excludes the stack frame for the string copy function. Earlier we saw that when a function in this case calls another function, in this case copy underscore args, it needs to add the return address on the stack. So the callee function copy underscore arg knows where to transfer control to once it has finished executing. From the stack above, we know that the data will be occupied upwards from buffer 0 to buffer 140. Since we can overflow the buffer, can also follow, so we can overflow the return address with our own value. We can control where the function returns and change the flow of execution of a program. So I have to have enough bytes to also overflow the return address. So I need to go to what the saved registers then. I have to like overflow it. I have to know how many bytes these are. Note that we can control the flow of execution by directing the return address to some memory address. How do we actually do something useful with this? What the fuck? That's crazy, bro. How do we actually do something with this? This is where shellcode comes in. Shellcode quite literally is code that will open up a shell. More specifically, it is a binary. Instructions that can be executed. Since shellcode is just machine code in the form of binary instructions, you can usually start by writing a C program to do what you want. Compile it into assembly and extract the hex. Characters, alternatively, would involve writing an assembly. For now, we'll use the shellcode that opens up a basic shell. So why don't we looking at actually executing this code? The basic idea is that we need to point the overwritten return address to the shellcode, but where do we actually store the shellcode and what actual address do we point it at? Why don't we store the shellcode in the buffer? Because we know the address at the beginning of the buffer, we can just overwrite the return address, the point at the start of the buffer. Here's the general process. Find out the return address. Find out the address at the start of the buffer. Find out the address of the start of the buffer and the start address of the return address. Calculate the difference between these addresses. You know how much data to enter to overflow. Start by entering the shellcode in the buffer, entering random data between the shellcode and the return address, and then the address of the buffer and the return address. In theory, it looks like it would, would work quite well. However, memory address may not be the same in different systems, even across the same computer when the program is recompiled. So we can make this more flexible using an op instruction. An op instruction is a no operating instruction. The system processes this instruction, it does nothing and carries an execution. An op instruction represented using \90, putting NMPs as part of the payload means an attacker can jump anywhere in the memory region that excludes a knob and eventually reach the intended instruction. This is what an injection vector would look like. You probably notice the shellcode memory addresses knob slides are usually in hex code. To make it easy to pass payload to an input program, you can use Python. Python-c print number of knobs plus shellcode, random data, number of random data, memory addresses. Using this format would be something like this for this challenge. Python C print knobs 30 plus shellcode, your shellcode, random data. I'd like the payload random data. Okay. And then the memory address. Wait, I'm getting confused. So this is the number of knobs plus the shellcode plus the random data, which is right here, the multiplied random data plus number of random data plus memory address. So then we just gotta figure out all this, basically. That's the whole goal. So easy. I'm cooked, man. I'm actually cooked. Let's see. Hold on. Just reading. So let's GDB -q buffer overflow. Alright, and then we're gonna do the Python course it didn't work. I always love when that happens. Alright. Boom. This is the first good thing. Come on, man. Hold on, maybe I restart real quick. Seems like I might have messed up. Let me make sure, like, hold on. I'm cooked. Hold on, man. Let's do this. Are you kidding me? Python, SC, print, dash, a dash, multiply 10, dash, okay, wait, yeah, that should work. What? Unidentified command. Oh, because I didn't do run. Oh my god. That makes sense. There we go. Okay. I feel like I'm already cooked. Definitely gotta quit this and just reopen this. Hold on, wait, I almost already broke it. Alright, let's see. So if I just try doing this, I'm actually fucking brain dead, man. Holy shit. Alright. Great. Let's try this. Okay, great. Let's try this. Great, great. Wait, that's actually good though. That's actually, I think, the right numbers. Alright. That's good. What's this? Do a little len. Nice. Len. Payload. This should be 158 bytes. Nice, nice. Alright. Let's see here. Alright. Yeah, I got an idea. Try doing this. I think. It's a new number. I haven't seen this one before. This is good. Alright, now let's see what the next steps are. Okay. Should be this. What? Bruh. I'm actually brain dead. Hold on. Dude's peeking over some mistakes. Type shit. Let's see, bro. This could be right. Hold on. Dude, wait. This is working. This is working. Oh, hold on. I'm actually doing everything right. Finally. So right here is our NOPS lead. And then if we go down to the 9, right here is our shell code. So great, bro. This is so great. It's actually fucking working finally. So bad. So bad. Alright, and then from here basically it seems like we bumped this final program. We should be able to do this from what it seems. Oh, hold on. pointer. What? I'm brain dead. I think this is something we do like over here. Like this. Okay. Interesting. Oh man, I'm so fucking like bad at this shit, man. Wish I could be better at binary and like fucking hex code and stuff like this. I already fuck up, so it's great. That's why it's holy shit I'm cooked. 4 times? I gotta get this shit over with, man. Oh my, bruv, I'm stuck on this fucking password. I need to leave here. Oh, am I doing it wrong? Yeah, bro, of course. I was doing fucking. Alright, now we try this beautiful command. Please. No. What do you mean no? No category? Yes, it is. Wait, what? Am I tripping? Hold on. What? Alright, let's see. Two, 9, 8. Trying to get to the next step, man. Let me just try this again. Oh, fuck. Try this. And then copy it. Try to debug this real quick. Oh. Looks like we got a show. Okay. Set it. REUID. But did I not get a show? Like what? actually so confused. No, I did get the show. Okay, that's what I thought. I gotta fix up the shortcut now. At least I'm in, man. At least I'm in. Alright. I think we got ours. I think this should work. I'm pretty sure. But we can confirm. Hold on. But don't tell me. What is happening, bro? No, bro. Like what? Am I geek, man? The hell? Bro. Dude, are you fucking kidding me? Dude, that's the third fucking box. I was about to solve this fucking shit, man. Oh my fucking god, dude. Just let me get done with this shit, man. That is actually fucking toxic. I think I was pretty much done too. Like actually, literally. 100%. Actually toxic. But if the shit's the same and I have the shell code, does it even matter? Because I already know everything is on the machine. I guess we'll see. Guess we'll fucking see, man. Actually toxic, bro. How does my machine close from this button? Extend machine timer. Like, bro. Actually getting griefed. I think I got it. I think I got it. I'm gonna get in that shit, man. Trust. Trust. Alright, first thing we do, we set our show. Bro. I'm getting griefed already. Set our shell code. Go into here, SSH. Done this so many fucking times already. User 1, boom, 10. I already know the IP too, that's the worst part. 10.10.230.80. I just changed now, of course. No? What? Oh, I swear I pressed the one though. Forgot the end, that's why. Alright, user 1 password. Alright, we're in. Let's do this right here. Oh, yeah. Just fucking right here. Are we in? Who am I? User 2. No, bro. There's no way I got user 1, bro. There's no... What? Aw, dog. Dog. I got user 1. Why, bro? That doesn't make any sense. I'm actually getting griefed. I'm all done right now. Let's see if this works. Run trust, please. What? Right, you're telling me it's not a directory? Oh, what the fuck? Forgot I'm selling this show. I'm tripping, bro. Gotta SSH back. Oh, hold on. I guess I gotta just exit, bro. This actually sucks. Like, what? My shell is cooked. Alright. So, what was I gonna do? Oh, yeah. This new show. Well, I don't actually need this. Well, hold on. Let me CD out then. Clear. And then I can use it, right? Because then the CD overflow 3. What? Hold on. I think this worked if I remember. I'm trying to get back in. Hold on. I think I have to do more shit once I get inside. I don't know really. There we go. Alright. So I gotta do. Try to do get. And 2. All right. Let's try this real quick. Wait, hold on. Wait. Let's fucking go, dude. I didn't even test if that shit worked, bro. I just assumed it didn't. I'm brain dead. Finally. Holy shit. Been on that shit for so long. 4, bro. Let's go check out 4. Maybe it should be a little easier now that I feel like I kind of understand what's going on. A little bit. Alright. Fuck, man. That shit was hard. For me. At least, like a little bit. 1080. Point. No, 230, 80. I'm tripping on the IP. Come on, man. Tripping on the IP on your first day. First day on the job. Tripping on the IP. Am I still like, what's going on here? Oh, I removed one of the towns. I was like, what? Alright. Man, I gotta get a new keyboard, bro. I'm telling you. This keyboard's cooked, man. Alright. Fucking finally done with that stupid fucking folder, man. I wish I could just delete it. Fuck, man. That shit was so hard for me. And this one's probably gonna be harder. Fuck, did I get there, man? 4. Alright. Let's see here. Okay, so I don't know why in 4 there's 2, but let's just run first off the code. .c. Alright, what is that? Oh, okay, this is like include studio.h, include studio.lib, void concat underscore argument. Okay, char array string char buffer 154. Okay. Equals doggo string cat buffer string. I feel like we're gonna be abusing that string cat, right? Because something like that. Concat underscore arg maybe. New word is s, which is string plus new line buffer return 0 integer main integer arg argument character char. Okay, concat. Yeah, it's gonna be either concat arg or the string cat. Is what I'm thinking. We're gonna have to find out what's going on here. Basically. So I mean, our best bet is if like it's 154. Let's see here. So 154. It seems like we have to take into account this right here. These 5 bytes. 1, 2, 3, 4, 5. 5 characters basically. It's gonna be 5 more bytes. So seems like our payload is gonna be 154 plus 5 more bytes, basically. Okay, so it seems like basically we quit out of here. GDB Q, and then we're gonna do buffer overflow 2 dot. Well, hold on, and not just this. All right, perfect. We're gonna do pretty much like that old Python thing we did earlier, but a little different. For C, there's number hope I can do this one easier. Alright, multiply 154 the bytes minus 5 minus 5 plus 8 multiplied by 2 plus 4 hold on. Boom, boom, and then we should get back. Bro, what? Hold on. What did I just do, man? I'm brain dead. What did I mess up? Probably one of these signs, maybe. I mean, I'm in GDB, but I do this every time. I hit type run. Simple. Alright, new word is doggo. Doggy. I could have done probably alright. So, gonna put this down again. Alright. Round 2, man. Round 2. Or 4, technically. Okay. Getting kind of confusion now. Alright, so we pretty much gotta go. Hold on. try this again. Pause. This should be right. I don't get it. Oh, I'm actually brain dead. Huh. It's weird. Let's try this. Okay. I see that. Hold on. Oh my god. I actually brain dead. Let's try this. Hold on. Oh my god. Just let me leave. Control D. Here. Alright. Do this. Oh no. It's not good. Oh wait. I forgot. Okay, I had to do this. Oh no, that's right. That isn't good though. But no, I think it is. Hold on. I think it's fine. There we go. And payload. That one's good. Okay. At least the ending result is good. Run. Where's our other terminal? There we go. Let's quit out of here. Well, actually, no, we'll stay in here. An accident. Should be this. Yes. Yeah, that's what we're looking for. Should we copy this? Alright, we gotta do this little thing here. I think I messed. No, I didn't. Alright. Invalid, yo. I did mess up. Oh wait, I'm actually fucking branded. Didn't mess up, but I'm not even in the right fucking terminal. Money RSP minus 200. Let's see if our shit is right. 3. Right, that should be. Alright, let's see. Making sure this is right. 0, 0, 0, 0, 2. Ugh. It's definitely not right. It's a little different. Fuck. Yeah, I knew that was gonna happen. So here is right. This is right. This is right. This is right. Alright, wait, we might be good. Let's see. Alright, let's do Control D. I think we have to do CD. No, wait. Yeah, no, that should be fine. We just quit. Yeah. Faces. Who am I? Yes, bro. Let's fucking go. Cat secret text. Let's fucking go, man. GG's. Shit was hard, man. Shit was hard. For me. Clean. That was a good one. Alright, guys. Well, we're gonna end this stream, obviously. Peace.